So on this problem, we want to compute the vector line integral um, f dot dr over curve C, and this vector field is the conservative field f equal to y times z plus y e to the power x, and second component xz plus e to power x, and the third component x times y. On the path, that is a line segment from point 1, 0, 0 to 1, 2, and 3. So let's say this problem is telling me that the field is conservative. I can check if the field is conservative also by taking the curl of the f. If I take the curl of the f, which is ijk and partial x, partial y, partial z of yz plus y to the power x, then xz plus e to the power x and xy. And this turns out to be actually the zero vector. Each term is going to be 0. And since f is defined in the entire R3, we're all good. And so that's the check for the conservative. Is it really conservative? So that's the first question. The second question is, okay, so now that I know it's conservative, what is important with conservative fields? They're basically their potential, their scalar potential. So let's try to find that next. Why is scalar potential? And scalar potential, it works like an antiderivative for them, and it's beautiful. And so now I'm trying to find the scalar potential. What do? Take the antiderivative of the first one with respect to x, because remember, this is the what I'm trying to do is to find a potential function f such that the gradient of f is equal to vector field f. So the little f and the vector field f. And so basically that potential function, when you take the gradients, the first component of f should be the partial of the little f with respect to x, then the second component should be partial with respect to y of f, and then partial with respect to z of f. And so this is yz plus y e to the power x dx, and then we do a comparison in respect to dy, and then xy with respect to dz. So try all three of them. Again, there are better methods that you will learn in DiffyQ, more reliable than this. But if you're very careful with this one, it's going to work out as well as the one in the DiffyQ. So what I do here is with respect to x, I get x, y, z. Then with respect to x, I get plus y e to the power x plus a constant, let's say c1. I did the antiderivative with respect to x, so c1 should contain the other two variables, which is y and z. Then do antiderivative of this one, xz with respect to y is xyz, plus with respect to y e to the power x, plus c2, now the other two variables again, the constant. And now here it's x, y, z plus c3, which is there, and the constant is the other two variables. Now what you do is you look at the terms that are in common. Here's in common, here's in common, here's in common. So I'm putting x, y, z. I'm starting to write out the potential function. And so first thing I do is x, y, z. then there's another term in common, and it doesn't show in here. So where it doesn't show, I have to make sure that the constant, it can be a constant in there, which it can be because it's function of y and x, and here also. So that's okay. Write the common term again once, and then take a look. There's nothing else left. In this case, if there was oddball functions out there, you just have to check with the constant of where they are not showing, basically, if they can be a constant in there. And then at the end, I add a constant, really a number constant in here without any variables in this case, basically. So now I found the potential. What scalar potential? This is my antiderivative, right? And so what I do is I go back and I say, well, I'm looking for finding the line integral from this point, 1, 0, 0 to 1, 2, 3. So I'm looking for the C such that line segment 1, 0, 0 to 1, 2, and 3. And so what I do is, all I need to do when I have the scalar potential to find a line integral, all I need to do is to basically use that scalar potential, which is x, y, z plus y to the power x, and I plug into it just like an antiderivative, except this antiderivative has 3 variables in it. And so you plug it in and you get for when you're plugging in 1, 2, 3 for x, y, z in here, what you get is 1 times 2 times 3, which is 6, and plus 2 e to the power 1. Then you subtract, and then this time is x times y times z, and you plug in 1, 0, 0, which is going to be 0. Then it's 0 times e to the, so it's 0 again. So the answer is 6 plus 2 to e to the power 1. So basically, I didn't have to do the entire process of taking the line integral. Again, if the potential function is given, sometimes you have to find the potential function, sometimes it's given. If the potential function is given, all you need to do is just to plug in the beginning point and the end point. Because conservative fields are path independent, that's what you can do, and that's why it's called the fundamental theorem of the conservative fields. That said, there are other methods of giving you the potential function. One of them is that sometimes they give you the level curves or level surfaces for the potential functions, and they ask you to find line integral from a point on one level surface or level curve to another level surface or level curve. And that should be, again, the same thing. You find the you evaluate the potential function at one point, and then you evaluate the potential function at the other point, and you subtract. That's it makes sense in physical properties of the potential function also, so you find a difference in there.